Hey guys, gonna try to do this in one quick screencast. Hopefully I don't have any interruptions from Leah. So, you might hear her in the background a little bit. All right. So I'm gonna just run through these really quick. This first guy should be screaming integration by parts at you. And the trick here, right, if you just tried to use F in general here, you were gonna be unable to do that. The key here is to notice the bounds from 1 to 3 and to say, oh, on 1 to 3, this guy is really the line 2x minus 4. Okay, so if you didn't do that, I'd pause me and try to do it now. And with all these problems, right, if you find yourself like seeing a different approach, pause it, try to do it, and then go from there, right? So anyway, this problem's really sine x times 2x minus 4 dx, which is a clearer parts problem, right? So we're going to set u to be an algebraic function, not a trig function. So du is that, and then we have 2 dx. And then that would make v sine, or dv sine x. It's going to be negative cosine x, I believe. Right? So then my whole integral up here would be equal to uv, so that's 2x minus 4 times negative cosine x, evaluated at 1 and 3, minus the integral of 2 times negative cosine x dx from 1 to 3 also. Well, this first part we can just evaluate, right? So when x is 3, this is going to be negative 2 cosine 3. That's 3 radians. And then we're going to have minus negative 2 negative cosine 1. God, there's a lot of negatives here. A lot of negatives to keep track of. And then over here, this is just going to be plus, right? These two guys become a plus. And then, so we're going to get 2 sine, I believe, right? Plus 2 sine x evaluated at 1 and 3. So it's still this business. Let's see, that's 3 negatives. Plus 2 sine 3 minus 2 sine 1. And again, these are 1 radian and not degrees. I think if you actually evaluate this, it's like negative 0.5, but I don't really care. You could just leave it like that. All right. For b, right, but do not evaluate an integral expression in terms of x, it would give the arc length of f over this interval. Okay, so we remember arc length, right? Integral from a to b, square root 1 plus f prime squared. Well, that's not so bad then, right? So this is just going to be the integral from negative 2 to 1. Negative 2 to 1. And if we look at this line right here, this is what? Y equals negative x minus 1, something like that. That's what f prime is on that interval. So we don't need to take any derivatives. That's what it is, right? So this is just the square root of 1 plus negative x minus 1 squared dx. There's nothing more to do with that. And as we said earlier, right, some of these things are kind of cumbersome to actually integrate, so a lot of them are just write but do not evaluate type problems. Okay, we'll continue alternating colors to hopefully keep things a little bit clearer. Let p of x equal e to the negative f of x. Yikes. Is the left Riemann sum approximation of this thing an over or under approximation? Well, let's consider it. So if we want to know if a Riemann sum is over or under approximation, remember we were always concerned about either concavity or increasing, decreasing. But we said, right, for Riemann sums, remember these pictures, right, no matter how, if something's always increasing, the left Riemann sum would sort of be an under approximation, right? Because no matter what, we're always missing out on these areas, whether we're concave up or down. Oh boy, that's not going to go well for this screencast. Maybe we'll have to do a couple. So no matter what, right, we were concerned about increasing and decreasing, not concavity for these guys. So we need to decide whether this thing is increasing or decreasing, which means we got to take a derivative. So P prime is going to be what? The derivative of that thing up there, which is going to be negative f prime of x times e to the negative f of x. Well, let's think about this. This thing here, always positive. E to the anything, always positive. F prime of x, if we think about on the interval 2 to 6, is always positive. So the negative of it, this is always negative. So we can say, therefore, P prime of x is less than 0 on 2 to 6. Well, I guess I really mean 2 to 6 on 2 to 6, right? Therefore, P is always decreasing, and so P always decreasing, and the left Riemann sum is an over approximation for a decreasing function. Over approx for a decreasing function, right? And you should be able to reason that out. We'll switch to purple, I guess, because sorry, I keep coughing. It's kind of a theme now. Let G prime be this business. Does G have any points of inflection? Justify clearly. Well, for points of inflection, we got to look at G double prime, right? And G double prime is going to be 1 plus f prime of x. Okay, so where does G double prime change sign? Where does G double prime change sign? That's where this thing has points of inflection. So we really want to know where f prime is -1, right? So we want to know where G double prime of x is 0, so we can see where it changes sign, which means f prime of x would be -1, and that looks like that happens at x equals 0, and what is that, 3/2? And you can look at both of them and see that we will indeed have a point of inflection there. Okay, good. Hope that made sense for this first problem. I know I went through that kind of quickly, but you guys can look at these answers and hopefully make some sense of my work. And again, I think the point I want to emphasize with C as sort of being a key point there, right, that we're looking for whether something's increasing or decreasing to see whether Riemann sum is an over or under approximation, not something else. We can never make any conclusions if it's both increasing and decreasing on some different portion of that interval. And we can never make any conclusions about the midpoint Riemann sum being an over or under approximation, right? Just by looking at the graph, right? We'd have to actually calculate stuff. Okay, so nothing with midpoints, nothing with trapezoids, only left and right that we can make conclusions. So you're never going to be asked to do anything else. Okay, let's move on. All right, the graph of f prime, the derivative of blah, 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 blah. Find the minimum value of f on the closed interval. Yikes. Okay, so what are my candidates? My candidates would be possibly endpoints and certainly possibly critical points. Okay, so which of my critical points could be a minimum? Only 6, right? So I'm going to work over here. Sorry if the strategy is crazy. Candidates 6. And then, right, because we're going from decreasing to increasing. Right derivative is going from negative to positive. -5 is a candidate, right? Because we're going left, we're increasing from the left boundary, so it's possible. Similarly, is 10 a candidate? We're increasing into the right boundary, so no. I think negative 5 and 6 are my only two candidates, right? And we know f of 6 is negative 1. F of 6 is negative 1, so we have to find what f of negative 5 is. So f of 6 is negative 1. F of negative 5, well, we know that the integral from negative 5 to 6 of f prime of x dx has to equal f of 6 minus f of negative 5, right? Some fundamental theorem for us. Oh, who wants to calculate this area? Not me. So what is that? That triangle over there is 1/2 of 5 times 3. This little half circle is half pi r squared. And then that tiny little triangle is 2 by 2, right? So minus 1/2, 2 times 2. Okay? And this equals negative 1 minus f of negative 5. And so I guess really the question is, right, does the positive area outweigh the negative area, right? So is this 15 halves here bigger than, what is this, 2 pi and 1? 2. And that's, yes, it is, right? Because 2 pi is, 6.28. That's 8.28. Oh, wait. It is more negative, right? Equals what? Negative 1 minus f of negative 5. Let's actually do this math. So what do I get here? Add that over. So I'm going to get 17 halves minus 4 halves. So 13 halves minus 2 pi, I think, is what I get here. Negative f of negative 5. Okay, so f of negative 5 is actually 2 pi minus 13 halves, which is going to be bigger than negative 1, I think. Right? Because that's going to be like 6.28 minus 6.5. Yes, so I would say f of 6 equals negative 1 is the min. Okay, that was a lot of work for that one. Let's look at B then. I've used a lot of my space here. Uh-oh. Where are we going to go for B? And maybe we'll work over here. Okay, let g of x equal sine of 3 minus f prime of x. Find g prime of 6. Okay, so what is g prime? G prime, I'm going to chain rule this, right? We're going to get negative cosine of 3 minus f prime of x times f double prime of x. So g prime of 6 is going to be negative cosine 3 minus f prime of 6. F prime of 6 is 0 times f double prime of 6, which looks like 2, right? That's the slope over there. So it's negative 2 cosine 3, whatever that is. I don't care. All right. Let y equals, Euler's method. We're going to need some space. Sorry, this is now so messy. We'll use different colors. Let y equals h of x be the particular solution to the differential equation. This thing, using Euler's method, starting at x equals 5 with 2 steps of equal size. Okay, so Euler's method, right? We're going to make our little table here. We're starting with 5. My delta x is going to be 1 because I need to use 2 steps. Right, my x values are going to be 5, 4, and 3. All right, and I know we start with 6. So dy dx when x is 5 and y is 6, oh boy. 6 minus f prime of 5, which is negative 2, over 5, 8/5. Okay, well, so this is going to be 6 plus the step size 1. Well, -1 actually. -1 is my step size, right? Times 8/5. Right, because we're going backwards, right? So what is that? 22 over 5? Something like that? Oh boy. This might be unpleasant now. Okay. Well, my dy dx then is going to be 22 over 5 minus f prime of 4. That's nice. That's 0. All over 4. Well, it's 22 over 20 or 11 over 10. So that means my final answer here is going to be 22/5 minus 1 times 11 over 10. Well, that's 44/10, 33/10, I think is my answer. 3.3. So fun. All right. And then, oh, there's one more. Particle. Okay, evaluate this and talk about what that... Okay, so we're going to talk about what this integral means. 0 to 10 of the absolute value of f prime of t dt. Well, we can evaluate that, right? That's just all those areas, right? So we already found some of these things. That circle's 2 pi, that little triangle's 2, and then this new guy that we haven't talked about is 4 times 2 times a half. It's whatever that is, I don't care. 6 plus 2 pi. I guess I do care. And what does this mean, right? So if we're taking the absolute value of velocity and integrating it, right? The integral of velocity is my displacement, right? The integral of the absolute value of my velocity is total distance traveled. Right? That's what that means. Okay. Good. Key takeaways from here, right? We got to know Euler's method. I don't know. There's not a whole lot. It's too interesting here. It's just a pretty standard AP problem. Okay. Good. All right. These next 3 guys are all past AP problems. The scoring rubrics are Googleable if you want, right? If you just search Joanna jogs along a straight path, I'm pretty sure that you're going to get that right away. I'll still talk through them because I wasn't there, but you can see sort of what the College Board would prioritize if you're so interested. Okay, so use the data in the table to estimate the value of v prime of 16. Well, I hope I get all these right. It's going to be kind of sad if I don't. Please email me if you find that I got some of these wrong for these next 3, where you guys can definitely check the answers. Okay, so v prime of 16, right? We would approximate that as v of 20 minus v of 12 over 20 minus 12, right? Sort of rate of change. You take the smallest interval you can, with 16's in the middle, right? And what is this? 40 over 8, 5 meters per minute squared, maybe. It's an M. All right, that's pretty standard. All right, B, same thing that we just did in the problem above, right? V of t in absolute value is going to be total distance traveled, right? So I'm not going to really go into that again, but total distance traveled is what that means. Approximate the value using a right Riemann sum. And notice these subintervals are not going to be equal at all. Okay, so that might be a little bit tricky for us. Right, this is an approximation. And so the right Riemann sum, right, we're going to get 12 times 200 plus 8 times 240 plus 4 times 220 plus 16 times 150. Yikes. I don't care what that is. I would just leave it like that, but that's what that is. And units would be, should just be meters, right? Okay. Right Riemann sum, that's all they're asking for. All right, our friend Bob is now riding a bicycle. It's kind of a non sequitur, but there we go. Find Bob's acceleration. Well, that's not so hard, right? This is Bob's velocity. So Bob's acceleration is just going to be 3t squared minus 12t. Well, that's about as easy as we get on this AP. A of 5 is going to be 75 minus 60, 15 whatevers per whatevers. Minute? Are these minutes? Yeah, who cares? And then D, based on the model B from part C, find Bob's average velocity. Oh boy, average velocity. Okay, right? So that's going to be the average value of his velocity function. So average value, right? 1 over b minus a times the integral from a to b, right? So we're going to do 1 over 10 times the integral from 0 to 10 of this business, which is, they actually want us to take this? A dumb problem. All right. And I know what you're thinking. You assigned it, Mr. Perlis. Okay, so this is 1/10, and then what do we have here? 1/4. Leah's currently standing over me, trying to intimidate me. I'm not gonna. Leah, I said you need to not interrupt right now. All right. We're looking at something like this. Obviously, it's 0 and 0, so you're just gonna, plug in this thing and. Who cares what this is? I'm not simplifying this at all. Okay, but that's what that is, right? And that's meters per minute or whatever. Okay? Pretty simple AP problem, right? Sometimes they give you functions, sometimes they give you tables. You need to be able to sort of work inside either context, sort of either set of given information. But I think most of you guys are going to be totally fine with that. Okay, let's move on to 4. So, slope fields. On the axis provided, sketch the slope field. All right, so if x is 0 on all these things, we're just negative y. So we're going to be -2, we're going to be -1. I guess we don't have to draw it in at 0, but I will anyway. And then here we're going to be +1. If x is 1, we're a little more complicated. So we're 2 minus 2, that's flat. We're 2 minus 1, so that's positive. We're 2 minus 0. Am I supposed to draw it in? Oh, the 6 points. Oops. Well, I bet they wouldn't take off if you drew too many. And then this guy's going to be super positive. Okay, so there we go. Slope fields, simple. Find the second derivative. Oh boy. Okay, so my second derivative here, well, that's just the derivative of this thing, right? So that's just 2 minus dy dx. And we know what dy dx is, right? We're gonna end up with this thing, right? Just plugging in dy dx in back into the second derivative now. Okay, and so in quadrant 2, determine the concavity. Okay, so in Q2, x is negative, y is positive. Well, if x is negative and y is positive, this thing's going to be positive, this thing's going to be positive, this thing's already positive. This has to be greater than 0. Concave up. I might write more on the actual AP, but I certainly would actually. But you guys sort of get my thought process right now. All right. What are we doing here? C. Let y equals f of x be the particular solution to this thing. Does f have a relative minimum, maximum, or neither? All right, so when they give us a differential equation like this is a good problem to focus in on, okay? You might be able to solve it and then look at the function and do all your calculus with that. That is more work than you're going to want to do. And you can't solve this one because you can't separate the variables, right? We can only separate the variables when we sort of have that multiplication business. If we add y to both sides, it doesn't work, right? Because then we'd have adding y, then we'd have y dx on the left. Like it's just not going to happen for us, okay? So you can't separate the variables for here, nor would we even want to try, because remember, to find out whether something's a relative min-max or neither, all we need to use is my first or second derivative tests. And we already have the first and second derivative. So don't do more work than you need to, right? So let's think about what dy dx is at 2, 3. Well, it's 4 minus 3, 1. Well, if the first derivative ain't 0, this is neither, right? So again, I know the temptation is there for you to go and actually solve this thing and find the original equation and then do all your calculus analysis on that. But you already have the derivatives, so doing that would be silly. So don't try. Okay, D, kind of a tricky problem that they love sneaking in on these differential equation type ones. Let's tackle it. Okay, so y equals mx plus b is a solution to this differential equation. Well, what does that mean? That means that mx plus b would satisfy this business, right? So that means that my slope m would have to equal 2x minus y, right? Because that's what that means, right? And what is this y? Y is mx plus b, right? So m would have to equal 2x minus mx minus b. And I know you're looking at this and you're like, this is a lot of alphabet soup here, right? But if you think about it, right, we sort of have this partial fractions type problem here, right, where sort of these guys are going to have to be 0, and these guys are going to have to be 0. So we're actually going to get a system here that's kind of nice, where I'm going to say, oh look, 2x minus mx has to be 0 because I don't have any x's to balance that out other than those guys. And m has to equal negative b. Well, we can sort of cancel out these x's, right? Factor them out. So 2 minus m equals 0, or m equals 2, and that would mean that b has to be negative 2. So I think that is a solution to this differential equation, right? So that y equals 2x minus 2 is a solution here that we just found. Okay, that's the most confusing type of problem though, right? But you have to realize like m is just the slope then, and then plug everything in. Okay, last but not least, look at this. Average value, related rates, it looks like. So fun. Okay, let's talk about the average value of the radius. So again, we haven't seen this too much on assessments yet. Maybe that's a hint, maybe it's not, I don't know. Haven't written it yet, so I guess it's neither. But the average value, right, is again the integral 1 over b minus a, so that's 1 over, what is this? 10 minus 0, right? And then times this integral, oops, from 0 to 10. 3 plus h squared dh. Oh, it actually wants us to evaluate this. Yeah, I don't really want to do this. Losing steam fast. So what is this? 1 over 200 times 3h plus 1/3 h cubed evaluated at 0 and 10. So, right, you can't leave it like this. You got to do some, you got to leave it so it's just algebra. I think it's that, right? Okay. Find the volume of the funnel. Oh my God, why are they making us do all this nonsense? Okay. The volume of the funnel, well, if we know the radius at every point, right, each of these little cross sections is going to be this little disc here, right? These little discs with height dh and this guy r, right? So we're going to have pi r squared dh. So what is pi r squared dh? That's going to be the integral from 0 to 10 pi r squared, which is this thing. There's a 1/20th in here, isn't there? Squared dh. So pleasant. So that thing is going to be pi over 400 times the integral from 0 to 10 of 9 plus 6h squared plus h to the 4th dh. Okay. Pi over 400 times 9h plus 2h cubed plus 1/5 h to the 5th evaluated at 0 and 10. That's awful. Pi over 400 times 9 times 10 plus 2 times 10 cubed plus 1/5 times 10 to the 5th. Yeah, I don't care about simplifying that at all right now, so I will not. And then lastly, our related rates friend. That's fun. The instant when the height of the liquid is 3 inches, the radius of the surface of the liquid is decreasing at this thing. Okay, so we have this formula. And I'm going to multiply this out so that we get a constant. So that's just going to go away. Okay. And we're just going to take a derivative, right? With respect to t. So that gives us dr dt equals 2h over 20 dh dt, or h over 10 dh dt. So in this particular problem, dr dt is negative 1/5, and h is 3, and we're looking for dh dt. So what does that make it? Negative 2/3? Somethings per somethings? Inches per second? There we go. Takeaway here, average value, important. Cross-sectional areas, important. Related rates, always important. All right. I hope this was somewhat informative. Please let me know if you have any questions. Yeah. Happy studying.